A while ago, we talked while we were creating the open source.siemens.com website and collecting somehow the memberships and so on. I got in touch with Dennis, and then I learned that we were also doing open hardware and having activities going on there. So that's why I thought, hey, that's a cool topic. And now we have Dennis here presenting us. Hardware development in the open source era.
Thank you very much. I appreciate the introduction, and it's not just what we do here at Siemens, but open source collaborators around the world, and I will share quite a bit of that this afternoon with you. Just to let you know, the presentation content is I'm weaving in development, open source development in probably the high end of hardware design. That's IC design. And going to take a bit of a step back retrospective to take a look at where this started for us before there was even an open notion of what open source was, and the impact it's having today on the development of interfaces, protocols, standards we use, and how we're influencing even the development of standards, their embrace of open source, and then to kind of show the era that we're in at the moment in the 2020s. A lot of complex systems are being designed around the world, and we're only really at the beginning stage of an embrace of open source that is going to give great leverage to the design teams around the world to invent these new next generation devices. So this will be probably a deviation a little bit from maybe the mechanical devices that you might expect from hardware or Arduino type of system, small boards that you may be familiar with. We're really looking at the impact of being able to democratize design in a lot of ways, and the steps that we've taken and even the contributions we've made at Siemens to help usher this along as well. For full background and my affiliation, while I am employed by Siemens Digital Industry Software and the Siemens EDA side of business, I also chair an IEEE Design Automation Standards Committee. I also just actually finished some meetings with Japanese and Europeans today for the IEC. There's a set of meetings going on this couple of weeks. We're all supposed to have met in Finland, but we are on Zoom again today, much like I'm joining you today here as well. I chair a group probably most of you don't even, or vice chair group most of you don't know. It's a feeder into the IEEE standards organizations. And then lastly, have been working with the IEEE to modernize its standards practice as a member of the IEEE SA open source committee. So in the beginning, open source came early to this industry, EDA, or electronic design automation. And with 20,000 plus developers of closed software solutions and marketing this around the world, we have many more who are contributing in the open source era as well. And we launched this really in the beginning, way before I was involved in a lot of this, but we were just recently, those of us who are involved in the current interaction with academia and standards. An article that was published last year really went through our steps to support public domain software. What we called it back then was shareware. We might be sharing computer decks of software programs still, on paper cards or magnetic tapes. We transitioned into an era of trying to massively share what we've been doing. If you like it, you can buy it. Not really open source, but it was more easy access than you might have been used to in the past, which evolved into kind of freeware with who knows what the rights for the use or resharing or embedding in your own solutions were. There was very limited disclosure of what rights one might have to the software. And in this time, maybe software was an easier thing to create, much less expensive than the $1 million machines that we used to run on. Of course, today, the mobile devices we hold in our hand nowhere come close to the limited power of those machines, nor the cost. But we've been in this for a while that I think we have some opportunity to share our heritage. The fact that we see a large uptake in open source projects. I don't even know how many get started today, but it's quite a few. And at the beginning of our time, and I wasn't around when the first transistor, I wasn't even born when the first transistor was created. But to bring students up to speed on how they might be able to learn device physics and the like, a class project started under the auspices of Dr. Ron Rohr began in the late 60s. And they developed this program called SPICE. Oddly enough, by the way, it's been one of the most popular programs in the early days of semiconductor engineering. It was free for everybody to use. So free, in fact, that other physicists were able to add their device models in, and we ended up with a lot of variations of the software, diverged quite rapidly, being able to embed the knowledge others had in trying to model transistors. The easy days of this are maybe kind of over, and certainly manufacturing a transistor today at the geometries that we are offered bring more device effects into account. By the way, Dr. Ron Rohr is still with us. While I'm the audience, I got a quick glimpse of all of you, 20s and 30s. You can imagine Dr. Rohr and his students as well, and their 20s and 30s. Last Thursday night at an industry banquet to award ongoing development and results based on this early work that we've done with SPICE. Dr. Rohr was in attendance, and amazing if we could all be as active and clear-headed in our 80s as he was. But we've celebrated a 50th anniversary of this. By the way, first called Cancer, and I think Dr. Rohr's wife convinced him that's not going to be a name you're going to want to have associated with your software for long. We had a lot of this work coming out of UC Berkeley, version SPICE 1, SPICE 2, moving from Fortran to C. But then commercial companies began to take this and also take the open source or the available source, the shareware, and create some commercial products. In this particular case, HSpice from Meta Software has ended up with one of the big 3 EDA companies today. Same with PSpice, Eldo, Spectre. And SPICE 3, the C version of this, was the last one that was released by Berkeley. And this has since migrated into and transitioned to commercial solutions. However, it also needed new models, and that continues as an activity in academia today. There's obviously a lot of research on device physics as we shrink down transistor sizes. So we kind of think of open source as maybe we've invented it, this industry. The first EDA, certainly the first open source EDA standard, SPICE or Cancer, is well anchored in practice that we have today. And we do have the likes of these pioneers who have allowed us to learn from what the value is of sharing, but also the value of investing in those organizations that can help bring this about. Academic setting for us in North America is one of the strong places where we anchor funding for the development of open source projects. But we've grown up from transistor level. The devices you enjoy today, if you've got an iPhone, probably or a new Mac, the M1 chip measuring probably over 100 billion transistors. We only got there through continued innovation in academic setting with a transfer into commercial setting. So while we had SPICE as our shareware model in the late 70s and into the 80s, we began to also develop digital simulation devices so that we could model that and run that on computers as well. So we really evolved from large scale into large scale integration, moving away from, and the ladies that you can see on this slide are actually going through a laborious manual process with X-Acto knives, cutting ruby lith, and that would end up as the ability to manufacture these silicon devices. And if you got it wrong, well, you just redesign it and repeat this until you can actually get the design right. But that wasn't going to last long because repeating this over and over again was a difficult thing to do. So it was noted at that time that what we really needed was a way of describing design languages. And we've got together as an industry group and invented the VISIC hardware description language known as VHDL, an IEEE IEC standard today. And we have colleagues that predated me, Al Dewey or Ron Waxman, as people to thank for ushering this in, along with generous grants from contract awarded by the U.S. government to IBM Texas Instruments and Intermetrics. Now that was a language and that was a standard, but another one was also emerging that actually handled more of the LSI, MSI devices and had transistor models at a more digital level, gate level models than the VHDL language had. And it became extremely popular as well. Totally proprietary, closed system. But when it was the company that designed this and invented it was acquired by Cadence in '89, shortly became an IEEE standard as well, is that they brought it in so that others could practice this. And so if you take a look at the model of where we are at moving into the 90s, we really had VHDL as an open standard, Verilog that transitioned from proprietary to an open standard, and with the open standard offered an opportunity for both commercial implementations and open source implementations to exist, and they do today. But as we were leaving the 1990s and the early 2000s, we began to work on a C++ base class library that really, in its first incarnation, was more open source in nature. It was shared under a license that has since evolved into adopting the Apache 2.0 license, but it had been done under some more emerging licenses that have since moved into more modern practice, pervasive in nature, to actually encourage commercial adoption as well. Companion to that was a standard that was created, an open source, open standard, IEEE 1666, which is also an IEC standard. At this level, System C was to be used for modeling block level devices and support system on chip endeavors that were just beginning at that time. If you recall, probably the first hand phones, the mobile phones that were coming out in the 90s were being designed with microprocessors that were described in RTL. And in order to get back into gates, which got us back into transistors, which get fabricated, we actually relied on open source academic work, things like products known as Espresso, to actually help seed the development of commercial technology. So through these decades, we've actually had a really good dynamic between academic setting, where a lot of work on open source is done, promote that into commercial practice, and evolve it for more hardening for commercial consumption. Now, this evolution that I kind of talked about begins with really a lot of proprietary things in the Verilog era and the VHDL era of these decades continue to work. And we knew that as we design things, we we're having problems testing it to make sure what we wanted it to do, it did, or what we didn't want it to do, it wasn't going to do. And so technology in this area led to our test bench area, where we landed on a dominant open standard system Verilog and a version of VHDL that embodies that. But what we learned in this time, and what I'll base some of our discussion of open source on, was the value of System C being widely available, easily made its way around the world quickly with downloads of it to be used on the computers that individuals owned, easily compiled C++ code. So from our vantage point, we can see open source is here to stay. And while I'm not going to go into a lot of the different open source activities that we've highlighted, even some in this design and test magazine from last year, it does serve as an understanding that this is a rapidly expanding, growing, and a great area to be in. But even more than that, we've been working to bring in the appropriate hardware licenses. As you build hardware and you open source hardware, the protections that one gets from hardware include patent mask right protections and the like. And the Apache 2.0 license that we were using to make it easily shareable information, more the code that we design electronics from, which is quite similar to the C or C++ or the Python you might use today. We needed something that that could also be adopted there, and so solder pad license, which many of you are probably familiar with, or a CERN license, hardware license, and its updates to it, have served to actually help promote and usher in more support of hardware elements as well. Well, as I conclude the talk today, I think you'll understand we have more work to do in this area, or more opportunity to exploit. But the industry has found that this is the good dynamic between the academic work that can go on and also the commercial work that can go on as well. It helps promote innovation and research, which is all good. And on the industry side, or even the health of an economy, a recent EU study by Dr. Knut Blint actually showed that a 10% increase in the number of contributors to open source projects could actually lead to an increase of EU GDP by about 95 billion per year. So truly, open source plays a key role in the vitality of world economies, and I think squarely sets the open source movement as one where not only you as individuals and technologists are concerned, but countries ought to have open source program offices, companies ought to have them. And we've seen a radical shift in being friendly, even from a commercial standpoint, and embrace there. So what happened in our methodology evolution, and this is where I come in with what Siemens had done. There were a lot of proprietary solutions and open printed standards, but these 1,000-page documents weren't by and of themselves going to actually allow groups to easily leverage their knowledge in this area and bring the methodologies, a common one across the working divisions, teams that they may have. And we introduced into the market a System C version of our advanced verification methodology and a companion one based on System Verilog. And while our competitors were steadily improving their closed source or their private solutions, we found that we garnered a lot of attention from users, and I don't think this is a surprise to any of you in the open source area. If you get something that sparks the interest of groups, these things can easily move around the world rapidly, like wildfire. Which led to us actually teaming with one of our competitors. We formed and created Ovium, taking the best out of the URM thread from one competitor and our AVM thread, ended up with OVM. Another competitor brought its work in from its verification methodology, creating UVM, and having probably the dominant big three market players all backing the same open source solution here led to really dominant use of this as almost the sole verification methodology. So this demonstrates why when Siemens started off with introducing AVM, it wasn't that we were going to take over the market, but we actually watched it coalesce around it. That really sticks with us today, that there's tremendous value in this, not only for bringing ideas to market, but actually allowing competitors to find the space to collaborate as well. For up to then, our ability to collaborate was probably more tightly bound with the written or printed standards like the System Verilog standard. So we have today a rich world where restricted source or private source or closed source is not the vogue, but the open source one is, and it lives along with an open standard. This is the other thing that we found out of this, is that what we really ought to do is to help drive the groups that are working on these open standards to also embrace open source, which in the last 5 years, they've done a great job to update the way they work and operate to actually promote that. At the same time, our VHDL friends were looking at what was happening with UVM, and at Siemens, we actually built a UVM framework that was good for them. We've got a couple other projects, one out of Europe, UVVM, and one from the principals that are in charge of the VHDL working group, OSVVM. And all of this also aligning with the new work that the IEEE has done to embrace open source. What you may not know is that for the 1076 standard, 1,000 pages of manual, a lot of it is package code that is essentially VHDL software. And it's tedious for anyone to have to take a PDF file, cut and paste. Of course, the IEEE made a lot of that available as source on a website you could get to without licensing terms and conditions that made it clear we could actually share code. And so what we started was Siemens has drove the IEEE to actually explore if it could embody open source. And as a pilot, the VHDL team actually took their package code and made it available all under Apache 2.0 license. The contributions that were made into the working group and have come from a lot of commercial sources are now available through download and under this IEEE SA open environment. And there's more to that as well. The hope that I have for IEEE SA Open is, as typical with a lot of foundations, they'll be able to start to also accept grants or gifts into it to help support the ongoing evolution, development, and maintenance of this work. Of course, since Siemens has started this track on open source in this area, we also know for our VHDL community, especially in aerospace and defense, Python has a large following, probably the largest programming language there, and also just a lot of libraries out there that are going to be more important for novel design emerging in the 2020s. We've created PyUVM as well as a UVM implementation of this methodology. So we haven't stopped creating, haven't stopped supporting an evolution, even in our thinking for open source. And if you're curious of what IEEE is doing for open source, it's not just about standards, although our push is to link it, had been to link it strongly with their printed standards work. You can go out there for individual projects as well. And we look to the academic community with a lot, which holds a lot of membership in the IEEE to exploit that, like other GitLab and GitHub solutions. We're not done, and the Verilog side doesn't enjoy the same footing as the VHDL team has. They still have standards. The UVM standard is now 1800.2, and the implementation of that remains back at the feeder organization into this. And to show how that kind of worked, it went from Siemens kind of open sourcing the code, leaving it on a site where you could download. We then teamed with a partner, created another website where you could download OVM. User companies took that because they had the right to, under the Apache license, brought it into the Accelera organization, brought the larger industrial companies together, and it sits there today under the Accelera open source area. And we think in time it ought to enjoy the same level of support as is provided by the IEEE. So what we've gained in all of this is really clarity in what we can do with this package code. If you can imagine taking these specs available from the IEEE or from the IEC, these thousands of pages with embedded code, cut and pasting, if you will, with yes, copyright held by the IEEE, but with limited understanding of how that could be shared. I might be able to download a copy for myself, embed it in a product. I may be given rights to share the binary version that I've compiled for my product, but do I have rights to share it with the next group and the next group? Does that group have rights to share it as well? And we really wanted that to be a more permissive in allowing for sharing. And all of this had moved into the Apache license. So this sets us up for something that's good. And so what actually happened in the world when we did this? And some research on that we conduct through Siemens is actually on language adoption. And what we can say that in 2020, we see the Verilog and System Verilog, where UVM is taking hold, has been quite popular language. VHDL coming in second in terms of the HDL languages, but they're still modeling in things like C, C++. For FPGA design, there's a little more constraints placed on a designer. FPGA are field programmable gate arrays, and the silicon structure is kind of locked, but as you decide how to use it, it will fuse the connections that can be reset and redone again. But the language there that's been dominant has been VHDL, continues to be VHDL, but we do see a little equality coming in between the VHDL and Verilog. By the way, the numbers of languages used could be multiple. People and the groups might be using both VHDL and Verilog. Hence, these numbers don't add up to 100 if you're doing the math real quick. But what verification language do they expect to use? And if you recall the slide back where we had the commercial implementations, a lot of those and the older ones are going by the wayside in favor of system Verilog. So that's good for the ASIC community. And for the FPGA community, there's VHDL had been dominant at the beginning of the 2010s, but we see a big growth in system Verilog, as well as, and here's an even larger growth in Python. So we're viewing Python as probably one of the next big things that will actually curry favor with this particular market. Hence, some of the work that we've done already with PyUVM in support of that move. But the base class libraries that have gone from commercial to this open source version, UVM, clearly struck a chord with users. This moved around the world rapidly when initially introduced. It became during the 2008 downturn, became a resume item. We had a lot of engineers in India learning it. It's a hotbed of practice today from the engineering community in India. And we see, near market domination for it, while the other methodologies like the Siemens work, the Mentor AVM work that we did in the beginning has kind of leveled off into more noise than where we see with AVM, with UVM. FPGA sees something quite similar, but I mentioned as well the VHDL community has been toying with its own options of OSVVM and UVVM, and also Python as just an aerospace and defense option. And the reason is, well, even finding people to program is hard enough. Finding engineers to work on a lot of these designs has meant reusing what knowledge you may have, and a lot coming out of university are steep with Python skills, but still UVM dominant in this area. Next week, by the way, Siemens, in working with the Wilson Research Group, will launch another study, and we'll see where things have gone the last couple years. But certainly, open source has had a tremendous positive impact in this industry. But where does it take it for designs of the 2020s? And in this one, we can go back to maybe recall Mark Andreessen talking about software is eating the world. But that software is demanding ever more advanced hardware. It's not just the simple compute platform that you might be able to run Linux on that is going to be the vogue of designs in the 2020s. Artificial intelligence and machine learning is really making all of these solutions smarter and faster. I can't imagine trying to perfect a photo image. The new Samsung or Apple devices that do that depend heavily on the neural networks and the silicon structures built in there, and then massive amounts of data. It's a data world right now. Just the amount of information at the edge, the sensor networks there, what compute can be offloaded, and we've been seeing a lot of low power AI enablement even at the edge. A lot of this is going to depend on new compute, new memory structure, new interfaces for that, but even more complexity when you get into the cloud and data center as well. The x86 devices of the past will in time not dominate the data center or the cloud. In fact, even the devices these things go into, you would think the classic companies that might be designing these things, whether it's the x86 ARM-based solutions, only to find that leading edge system companies are becoming the SoC designers, are becoming the system designers. And as a sample, logos of companies that have announced their own chip implementations today, leading to what is probably one of the fiercest competitions for silicon. Read reports that silicon is sold out through 2023 just to satisfy the demands that companies like these are placing on them, from autonomous systems, autonomous drive, uh, uh, thinking systems. It's truly one that's expanding. And this market opportunity, which I don't think any of us could have predicted, the growth will conclude this decade at probably an over a $1 trillion market, will be driven by those who can actually develop the systems on the edge or the cloud or in support of 5G. And this is not going to be just by design done through use of one's own invention, but the sharing of stuff, which is going to be, I think, heavily rooted in open source. And to that end, I probably will leave and focus on two things here, but knowing that there is a wonderful opportunity for all of us in the future. One is RISC-V based designs. If you've not heard of this, there's just about every university is working on things that might be RISC-V related, or the Open Hardware Group. By the way, RISC-V is a Linux Foundation activity. Open Hardware Group, which is an Eclipse Foundation based activity, is trying to down select from the different variety of chips that are out there, a lot designed in a university setting, which I'll talk a little bit in a moment. But there's other ecosystems underway as well. The United States government is funding quite heftily universities to actually work on open design solutions. There are open source FPGA Foundation on an open FPGA solution. So that's good news that there's, from an open source perspective, opportunity. On the interface protocol side, probably still stuck in maybe the way IEEE had looked at things at a specification only phase, or only printed document. What we need to do is to work on them to express their interfaces in language or ways that can be analyzed easily and easily shared. And through a lot of work by government agencies, we are moving into and encouraging this to actually happen. You can look at the Toolbox Initiative, the United States DARPA Defense Department, the European Processor Initiative has been looking at options that it can do as well. And some of this is related to just trying to have one's own sovereign designs and to make sure that supply chain protection and engineering protection is there. So even open source, and this probably means even in geographies, opportunities that might have not been or had not exist or easily would exist. And even an example of that is the Schottky project, which has led to the Digital India RISC-V microprocessor group. So RISC-V actually is a Switzerland-based group redomiciled out of the United States in Switzerland. It really standardizes on an open source instruction set architecture. x86 and ARM, other proprietary architectures are closed, although you can gain access and modify them with royalty fees, which a lot of the large companies do. Yet the RISC-V ISA has seen a lot of uptake, not just in the university, for learning purposes, but actually in commercial ecosystem development as well. And so where the red box is here, I've kind of talked about the opportunity for open source hardware from what we can do for RTL or DV for design verification. There are implementation activities underway. Have not shared. Google is a huge supporter of paths into silicon fabrication here, along with a lot of the other alliances that are sister and partnered with RISC-V ecosystem. And I'd suggest you check them out. Now, in the research we did at the Siemens Wilson Research Group study, we actually found 23% of both ASIC and FPGA designs are already incorporating RISC-V processor. Knowing that on the FPGA side, these are built in, so some FPGA suppliers have gone with RISC-V. Predominantly, the balance are ARM processors. For ASIC and IC, again, dominant supplier today is the ARM processor, led in the early days by the likes of mobile manufacturers, Nokia and Ericsson. But things are changing. And one of those is actually the work that's being done by the Open Hardware Group. They actually have a mission. This is an interesting one where they want to bring hardware and software designers together to collaborate in open source cores. So there are many open source cores available around the world. They've happened to have selected ETH Zurich's Pulpino RISC-V core, not just ETH Zurich is working with University of Bologna as well to work on this, but they realized that, and so the thing here is also building industrial grade UVM environments out of this as well. So there's related IP, PCI, MIPI, other cores that are important to design, and related IP. This is something that's in progress. We hope Open Hardware Group offers clarity here. And at the same time, they're working with commercial and open source tool supporters. And on the commercial side, the Siemens formal verification team has been working to make sure that commercial tools adhere to the quality of the opportunity and the cores that are being selected here. So lastly, here are some links. Some of the links. There's certainly there's many more in this in open source for EDA that are impacting hardware design today. And I'm sorry I can't be there with you guys today, but certainly there's a hotbed of activity, probably even a few blocks from where you guys are meeting right now. Thank you.
Thanks a lot, Dennis. Impressive to see. I was using Spice as well, but I have not been aware about the time when it has been created. We can just take one question during the time constraints. The question is, do you see a tendency that companies make their schematics as well open source like they do it with the parts of their software?
That yes, I do, and I didn't touch on that. Schematics is probably, and even the artwork for PCBs and the like. I think that trend is there, and there are format files for that. Even on the ICs, looking at ways of even making hardened ones that may even be for particular process. There's work in that area as well. As I mentioned, Google with working in that area. So whether it's the schematic level, board layout, or even IC implementation, I certainly see that as part of open source deliverables.
Perfect. Thank you very much, Dennis, for joining us. I wish you a nice day, and hope you see us one's life.